So today we have, before starting the lab, okay, I'm gonna just highlight the negative half-wave rectifier, okay, because we're gonna experiment with it in the lab today, okay, and also the negative clipping. We saw problems which the diode can clip from the positive side of the wave. Okay, we're gonna see today how to analyze analytically a negative clipping, a diode that can clip from the negative side of the wave, and also the two-way clipping to construct a circuit that can clip either way, from the positive half cycle and the negative half cycle of the input signal. Okay. Okay. So let's let's first analyze the diode negative half-wave rectifier. Okay. So sometimes you want negative DC. So you wanna convert from AC to DC, but you want a negative DC. Okay. Of course you can, just clip the inputs, for example, flip them. Okay. But sometimes you have in the same circuit a positive DC and a negative DC, which will be harder to do such flipping. Okay, especially if one of them is a ground. So we want to generate directly negative DC output. Okay, and what we only want require to do is just flip the polarity of the diode in the half-wave rectifier that we just studied last lecture. Okay, so in last lecture, this diode here that you can see in front of you on the screen. Where are my gloves? Yeah, this guy was in the previous lecture was connected like this. Exactly the same circuit, although the polarity now is different, is flipped actually. So this should generate a signal that has a negative average or a negative DC. Okay, so let's analyze the circuit before we go to the lab and see that with our own eyes on the oscilloscope. Okay, so basically consider it as a problem, and it's required from you in this problem to sketch VO, the voltage on the resistor, versus V input, and the VD, the voltage of the diode, also versus V input. And remember, VD is always from the N to B. Okay, that's fine. Again, we're gonna look at the input and analyze all the possibilities that we can encounter during our solution. So in the input, we have a positive half cycle and a negative half cycle. So let's start by the positive half cycle. In the positive half cycle, we can look at the circuit in that way, just a variable battery, a variable input, with that guy here, the diode, and our resistor. And always the output of the battery is positive. I mean, all the time this node has a higher voltage than this node. This is actually the job of the voltage or the battery, to make a difference between its terminals. And in that case, in the positive half cycle, this difference is positive all the time, or zero at this point, or this point at the edges. Okay, with that polarity here, the diode is always reverse. So it's off all the time. And we know, there is a restriction here, because we assume always that the maximum input in reverse is less than the diode breakdown voltage. As we saw yesterday, if the breakdown is small, then you might have a clipping, okay, in the negative. Here it will be in the positive. And we're gonna see that again in the experiment in the lab. Okay, so let's continue now. So the diode is off. So ID is always 0. I mean, the diode can be considered as open circuit. So VR, which is equal to VO, which is ID multiplied by R, is equal to 0 all the time. From Kirchhoff, this is V input, this is VD. So V input plus VD minus VO. Be careful with the directions here. Okay, so V input is upward, VD is in that way to the right, VO is upward. So V input will have the same sign as VD minus VO equal to 0. VO is 0, so VD is equal to minus V input. And VO is always 0 in the positive half cycle. Good. Now let's do the negative half cycle. So before continue, let's draw this just to make it complete. To complete everything. I just need to, I'm gonna need some space here. Okay, so VO is 0 all the time. So from here to here, VO is 0. Just 0 like this. And VD is equal to minus V input. So take any value and just multiply by minus. So for example, at this point, whatever the value is, for example, 1, then VD will be minus 1. This is, for example, 2, VD will be minus 2. This is Vmax. So VD will be minus Vmax, and so on. So basically, flip this dome. This half wave will be flipped. That's it. So here too, yes. And we know that this is correct. We gotta now check that we are correct on the right way, because we know that in the most of half cycles the diode is reverse, so its voltage should be negative. And yes, all these values are negative, so we are in the right way. Now let's go to the positive half cycle. We finished now the negative half cycle, which is very good news. If this is exam, for example, you take half of the marks. So in the negative half cycle, Now we have a trick here. We have, you know, a problem. We usually deal with, you know, with reverse and forward conditions in some particular way. I will explain it now. So let's do that with another color. For example, that's fine. When we say reverse and forward, okay, let's have the two conditions. So let's have a diode like this, and a resistor, and a battery of 5 volt, for example. Any voltage, any positive voltage. And this is another condition, same battery, but the diode is flipped. And also 5 volt. Okay? So in this circuit, this number one, this circuit number one here, the diode is forward, no doubt on that. Here the diode is reverse, also no doubt on that. But in both cases, you will see that, I'm sorry, yeah, the diode is reverse. Yes, the battery has a voltage, positive voltage input. It's positive. Only the diode is flipped. How about these ones? Another color. And -5. Is this forward or reverse? If we look only at the which is close and which is far, the positive polarity here, the positive terminal of the battery is close to the B. The negative terminal of the battery is close to the N. But the battery value is -5. If we just, you know, translate the math, we will say that this point, the positive terminal, is higher than or greater than this terminal, the negative terminal, by -5 in math. So it's actually, in fact, the opposite way, that the negative is larger than the positive by 5. So it's better to draw the circuit like this. Same circuit, but I will flip the battery and flip also the value. It's 5 volt. This is exactly equal to this. They are equal. They are equivalent. I only flipped the battery and its sign, the value, the sign of the value. Instead of negative, become positive. But be careful here, because the battery the voltage of the battery direction is from negative to positive. So it was in that case in that way. Now it will be flipped as well. This is very important, because this will affect your Kirchhoff analysis, Kirchhoff voltage law. Okay, so let's go back to our circuit. And let's draw the circuit in the next. So we have here the diode, we have here the battery. I'm sorry, the resistors. This is the output, and this is the ground. Nothing changed. Now the battery is something like this, and it's changing because it doesn't have a constant value. But all the values here are negative. Something equivalent to this. So what I'm gonna do, and the direction of the battery is in that way, from the ground to positive. So I will draw it in that way. And it's still, yeah. Everything is the same. I just flipped the polarity of the battery. And I know now all the values are positive now, but the positive polarity is towards the ground, the negative is higher now towards the diode. And the direction now become in that way. And I will call it V input dash. Okay, now we go back to the drawing, this plotting, the signal stuff here. So this signal here, this input signal was drawn or plotted based on some assumption. This assumption is, we assume always in positive half cycle and negative half cycle, we assume always that the positive polarity is here and the negative polarity is here. We assume always that this point has a greater value or potential or voltage than this point. In the positive half cycle, yes, it has, yeah. The voltage difference is always positive. In the negative half cycle, we can still say that this is greater than this, but by negative values, which in fact is the opposite, right? So when we draw this signal here, we assume always the arrow is from the ground to this point. With our new flipping here, with that, when we flip the arrow, we should also flip the values. And we call this V input dash. And we're gonna deal with V input because it's positive. We like positive all the time, okay? So, and this is my way of analysis. Of course, you find many other guys that, you know, deal with the original situation, but I don't like this. I see this is more direct and more convenient for any student. This is my point of view. But anyways, so in the negative half cycle, instead of going with the default, which is the positive polarity is larger than the negative polarity with negative value, which is nonsense. So let's go to the direct way. The negative polarity has larger voltage than the positive polarity. So we just flip them, and we flip also, since we flipped the direction, we also flip the values. And we make it just dashed like this. And we will deal with the circuit in that way. So let's continue our analysis and see what we have. So we flipped. Now the circuit is in that way. You have a battery that have a variable voltage. And this battery has negative here and positive here, opposite to this one, the original one. This is Mr. VD. And here is Mr. VO. Somebody may be still not convenient with this. Okay, that's fine. So we can do another trick. This is just a series, right? So we can basically flip on. We can just continue with this. That's fine. We will do this flipping in another circuit, but let's continue with this. So basically here we have this situation now. So this circuit here is exactly this one. Okay. Although the diode is reversed now. So now the negative terminal is close to the N terminal of the diode. The positive terminal is close to the B terminal of the diode. So this is forward. So the diode is forward. And it needs 0.7 in order to operate. So we have two cases. When V input is less than 0.7, the diode is forward but off. So ID is equal to 0. So IR is also equal, because ID is just IR. You have the same current. So VR, which is VO, equal to 0. Now let's do Kirchhoff. Vn dash plus VO minus VD equal to 0. Look at the, so if this is the directions, so this is going down, so it's going, this is going up, so they are in the same direction, so they have the same signs, but V is opposite to them in direction. VO is luckily 0, so here VD is equal to minus Vn dash. Remember, Vn dash is just minus the original V input. So we can say also that Vd is equal to V input. Okay. Now, case 2, when V input is larger than 0.7. With this, the diode will be forward and on. So Vd is equal to 0.7. One of the unknown is solved. And let's apply Kirchhoff again. So by Kirchhoff voltage law, we have V input dash plus VO plus minus VD equal to 0. So VO is equal to VD minus, yes.
Can you, why is it VD equals minus VN? Isn't VD negative? So if you take it to the other side, they're both positive?
So
On the
VD
KVO.
here?
Yeah, because you have VN plus 0
VN
is,
dash.
yeah,
VN
VN dash plus
So,
0 is minus VD. So how is it
so
VD equals negative VN dash?
I am very sorry. I am very positive. I am very sorry. Yes, you are right. You are absolutely right. That's right. I am very sorry. Yeah. Yes. Okay, thank you very much. Thank you. Okay, so let's go back here. So now V input, V output, which is our unknown now, is equal to VD is 0.7. So let's do the substitution directly. 0.7 minus Vn dash. Okay. Good. We have finished basically the negative half cycle analysis. Now let's apply, let's draw, let's sketch what we got here. So we have here a point at which when V input, so our transition point, where we have two regions, the regions at which V input is less than 0.7 and the region at which V input is larger than 0.7. So we look for, first we should look forward, I'm sure we should look for these regions. When V input dash, now we are dealing with V input dash, not V input. When V input dash is lower than or smaller than V 0.7, and when V input dash is larger than 0.7. So we go back here, okay, and you know it's just a sketch again, so you can choose any arbitrary point, just something acceptable. Okay, let's say this is 0.7. Let's say so. That's fine. And do you draw this nice line here? Okay. So yeah, this is the cross section here. So good. This should be it's not good. Okay. Remember, we are dealing with V input dash now. Okay, not V input, not the original V input. So, in this region and also this region, V input dash is less than 0.7. So basically, VR will be 0. And let's continue with green here. And VD will be equal to V input dash. VD is equal to V input dash. So we go back here. Whatever V input dash in these two regions, VD will be just a copy and paste. 0, 0, 0.1, 0.1, 0.2, 0.2 until we reach 0.7. This is just a copy and paste here. Again, 0.7, 0.7, 0.5, 0.5, 0.3, 0.3, 0, 0. Again, this part here is just copy and pasted here. If you still like the original V input dash in the negative half cycle is just equal to minus V input. So VD will be equal to minus V input. So this is Mr. V input. So take any value, multiply by minus 1 or minus, okay, and draw it here. So both negative 0.1, it will be positive 0.1. Negative 0.2, positive 0.2. Negative 0.7, it will be positive 0.7. And again, the same thing here. So take this part and flip it with positive. That's it. Or deal with V input dash, whatever you like. And again, this V input dash stuff is something that you cannot find people do it in that way. I don't know. Maybe I'm the only one that do it in that way, but I find this more convenient, at least for me, because I don't like negatives. Okay, and that's just personal preference. Okay, so we have now drawn or plotted or sketched V input dash. I'm sorry, VD and VR. Now let's go to the region at which V input dash is larger than 0.7, which is this section from this point to this point. And in all that region, VD is equal to 0.7 constant, like this. This value is 0.7. Okay, and VO is equal to 0.7 minus V input dash. So, read now. This is V input dash here. So take any value of V input dash, multiply by minus 1, then add 0.7 or 0.7 minus whatever. So for example, 0.7 minus 0.7, it will be 0. 0.7 minus 1, it will be minus 0.3. 0.7 minus Vmax, this is Vmax, this will be 0.7 minus Vmax. Again here, for example, 0.7, so 0.7 minus 0.7 will be again 0. So you will have the same, this dome here, this stuff here is exactly this one. And of course, this will be repeated in other cycles. So in the input, you have positive half cycle, you have negative half cycle, you have positive values and negative values. In the output, you have only negative values. So this is negative half wave rectifier. So in principle now, you can generate out of AC, you can generate, as we said yesterday, like half a DC, 50% of the a DC. some signal that has one direction. It's not like the input. So in the positive of cycle's direction is that way, the negative of cycle's direction is that way. No. Now we have one direction which is negative all the time. Okay. Any question, guys, here before we go forward? Okay. So one last thing to do.
Well, I have a question.
Yes.
Since the diode's on, it can't go past 0.7 in the negative half cycle?
No, it can't.
Okay.
When the diode is become forward, it will take its 0.7 and that's it. Okay. If you solve a circuit, okay, and the diode was forward in that circuit, and you assume it's on, for example, or whatever assumption you have, then you will find that the diode is taking a voltage of, for example, 1 volt, then the assumption is wrong. Because according to the constant voltage model, the diode voltage cannot exceed 0.7. It's 0.7 and low. It can even be negative, but it can't exceed 0.7. If you find in your solution that the diode has a voltage larger than 0.7, this is, you have something wrong. Either the assumption itself is wrong, or you have something in the calculations. Okay, one last thing before we go forward. Let's now calculate V average, just like yesterday. Average DC value. Okay. So the positive half wave rectifier, the output is approximated in that way. And this, of course, will continue, and we find that the VDC or V average is equal to V max over bar. And here we are using the ideal voltage model, which makes the solution very easy, by the way. But I like to do the harder ones with you, so you can, because this is the most convenient, most well-known way to deal with diodes, with the constant voltage model. Now with, so this is positive half wave rectifier. The negative half wave rectifier, we have something very similar, but in the negative regions now. And can anybody tell me what would be the average value here? Any guess? Yes. Minus Vmax over bar. So the calculation of yesterday, this was the integration from 0 to pi sine theta d theta plus pi to 2 pi 0 d theta over, I think 2 pi, yes, 2 pi. This will be exactly the same. So let's do it with another color. Or not exactly, something very similar, not exactly the same. So it will be, now from 0 to pi, it's 0. It is the opposite. So 0 d theta plus, from pi to 2 pi, sine, not minus sine, sine theta d theta. Because remember, the original shape of sine wave is like this. in one cycle. So this is sine from 0 to pi. This is also sine, but from pi to 2 pi. Okay, this is very tricky. It's not here minus sine, no, it's still sine theta, but theta itself from pi to 2 pi. With these values of theta, the value of the sine here will be negative. So you don't need to put negatives, okay, or negative sign. So this is very tricky, okay. And again, we divide by 2 pi. Okay, so, and of course there is V maximum. Yes, V max multiplied by this. Okay, so this will be give you minus V max over pi. Is it clear? This final step, this tricky step, you know, that it's a sign, not negative sign. Is it clear for all? Okay. Okay, so yeah. We also we saw positive clipping, okay, where the clipping was happening in the positive. So the output of the diode was something like this, and in the negative it was the same as the input. This is positive clipping. Now how about negative clipping? If we want to make a clipping in the negative here. Okay, so this is a circuit that will do that for you. So let's analyze it and see and prove actually that we're gonna make a negative clipping. Just, you know, remove also junk here. That's fine. Okay, so let's go back. Now we have a diode here and a battery VB. Okay, and the input like this. It's changing in that way, in a sinusoidal way. It can be actually anything. It can be even a triangular wave or, you know, a square wave. This will not change the analysis. And that's also a tricky thing because we are always dealing with sinusoidal, but I can in the exam give you, for example, triangular wave or, you know, square wave. It should be the same. And by the way, when you struggle with some circuit problem, do it in multi-sim. Just to construct the circuit, okay? If it's AC, put AC value, and if it's required to plot the outputs, you know, put some oscilloscopes and, you know, have an idea about what should be the output, then try to rationalize, we can say, make some logic, trace back from the output that you see why we get that output. Of course, this will give you a very good idea about how to solve the question. If it's just, you know, a problem with numbers, put voltmeters and ammeters, you know, and measure the current and the voltage. So this will also give you a very good idea about what should be the solution. Okay. So let's do that. Let's start first by the positive half cycle. This guy here. In the positive half cycle, we can draw the circuit in that way. Here I'm assuming that VB is larger than is positive, okay? Because of course the solution may depend on VB. We can visualize the circuit in that way. You have here V input, which is variable, and this is small resistor here. Good. Let's choose VB is equal to, for example, 1. Okay. Now, it's not very clear to us if it's forward or reverse. Why? Because we have basically two batteries. But we are sure that the two batteries has positive voltages. So the directions of the voltages of the batteries are, you know, is not a changing. One is upward and the other is downward. So how about moving VB? We want to know if it's forward or reverse. So this is a series, very simple series circuit. And doesn't matter where is the location of each element in the series circuit. So just move VB from its branch now toward V input. So we can basically draw this circuit in that way. This is the ground. Don't forget about it. This is VB and this is V input, and V input, as we say, is a change, but it's positive. All these values are positive. It's a positive cycle. Now we have a very good idea because we can model that actually in some way, somehow like this. And this is positive battery or positive source. And we are now very sure that this is a reverse bias. A reverse bias. This is clear or not? If it's not, please let me know. This is clear? Should be clear. Thank you. Okay, so when it's reverse, then it's off. So that so ID is equal to 0. So VR is equal to 0. Remember, we want to draw or sketch VO, which is in that way. So let's do Kirchhoff here. So you can assume the current in any way, that's fine. So basically, I'm going to assume the current in that way because the diode current flow from B to N. So this is VR, opposite to the current direction. So we have V input, the Kirchhoff voltage law, V input plus VR minus VO equal to 0. VR is 0, so VO is basically equal to V input. Now let's sketch that before going to the negative half cycle. I need some space here, so let's. So VO is equal to V input. So just take this dome here and copy it and paste here. If you want to do point by point, which is impossible because you have infinite points here. So 0 here will be 0 here, 1 here will be 1 here, Vmax will be Vmax, Vmax minus 1, Vmax minus 1, 0 again 0, and so on and so forth. Okay. And this should be VR, I'm sorry, VR, yeah. And the VR is equal to 0. Let's do it with another color. 0. Like this. Now we go to the negative half cycle. Let's do it with red, for example. So number 2, negative half cycle. So let's draw the circuit first in the negative half cycle and see what we should do to understand it well. This is Mr. VB, which is positive again. This is R, okay, and V input, and it's changing. And this is VO. Now we have the same issue as, you know, the negative half wave rectifier, because the input is negative. So this battery here has negative values. Also, the voltage direction is upward. So this is a ground here. So we're gonna flip it down. And call it V input dash. And now it will have positive values. And go back here. So this is the original V input, positive and negative. And the direction is always upward. Now we're gonna have V input dash here. With a opposite direction, downward. Downward. And we're gonna use V input, I'm sorry, this is, yes. And we're gonna use V input dash, not V input, not the original V input. Okay, that's fine, let's use it. We already did the positive clipping. The positive clipping circuit was something like this. So can we convert this one into this one? Because we already know how to deal with this one. How to know the, you know, the minimum inputs that will turn the diode on, and so on and so forth. So this is positive clipping. Yes, we know. And yes, we can convert this circuit into this, you know, this shape that we already know. So basically, I just, you know, draw it for you. What I will do now, I will just, let me show it very clear. So this is a circuit, okay? I will take this node here and just flip it in that way. So if you draw it in that way, it will be exactly, if I just, you know, this is the original shape again, okay? I will drag the circuit from that node, the ground, up. So I will flip it. So it will be something like this after the flipping, which is exactly the same circuit that we solved with positive clipping, but now the ground is just above. Okay? So I will take this node here, drag it up, which is really valid, 100% valid. It will keep everything the same. When we drag this up, this will be upward, yes, this will be upward, yes. This is the resistance, and this guy will be like this, Okay, and positive still. And remember, this was the original direction of VO. You should and must keep the direction of VO. So VO was from the ground to this point. From the ground to this point. If we look, this circuit is exactly this one. Of course, this is in series. You can just get the diode up if you wanna, make it more convenient for you. You can make something like this because they are in series, no problem. Oh, I'm sorry. Okay. And if you remember, we said that when the diode is on, to solve this circuit now, the diode will be on if it has 0.7 here, and the voltage difference here is VB. So at this point, the input will turn the diode on when V input dash equal to V input minimum, the input dash minimum. The diode will just turn on. What does that mean? ID is still 0. But VD is equal to 0.7. This is VD. So let's do Kirchhoff voltage law. Vn dash min. Okay. The input at which is that will turn on. Minus, remember this is VO. You can assume the current in that way. So this is VR. So Vn dash plus VO minus VR equal to 0. Since ID is 0, so VR equal to ID R equal to 0. So from here, VO is equal to Vn dash minimum. And remember, VO is equal to minus VB minus 0.7. Look, VO is downward. Those guys, VB and 0.7 is upward. So it's opposite. So VO is equal to minus those guys. Minus 0.7 plus VB, or minus. Minus VB minus 0.7. Oh, VO is equal to minus V input. I'm sorry, minus V input dash. Yes. Kirchhoff here, V input and VO has the same sign. So if V input dash minimum goes to the other side, it will have a minus sign. So from this, Vn dash minimum equal to VB plus 0.7. If you go back and see the solution for this circuit, this circuit makes the clip or the clipping at 0.7 plus VB. Exactly like this one. That's why I convert it in that shape. So you can check. It will have the same solution, exactly the same solution. Although V out now is flipped because of, you know, it's a new circuit afterwards. So let's draw that. Okay, so before we go forward, just, you know, now we knew when the diode will be on. Okay, so we have again two regions. When V input is less than V input dash, Vn dash minimum, which is equal to Vb plus 0.7, the diode is off. So Vr is equal to IDR equal to 0. And if we make Kirchhoff now, it's Kirchhoff voltage law, Vn dash plus Vo minus Vr equal to 0. This is 0. So Vo equal to minus Vn dash. The second condition, when Vn dash is larger than Vn dash minimum, which is Vb plus 0.7, the diode is on. So Vd is equal to 0.7. So Vo is equal to minus 0.7 minus Vb. If we apply Kirchhoff again, Vr is equal to Vn dash plus Vo. So it's equal to Vn dash minus 0.7 minus Vb. So let's apply this on our to plot. Let's plot them. So in the negative half cycle, which is positive for V input dash, first search for the transition point, the point at which the flipping will, which is on, which is off will happen, which is V input dash, which is Vb plus 0.7. So if, for example, Vb is equal to 1, so assume this is 1.7, this point here. So go forward like this. So this is a transition points. So in that region and that region, the diode is off because the input is less than Vb plus 0.7. So Vr is 0. Let's draw Vr. 0 and 0. And the Vo is equal to, where is it? Minus Vn dash. This is Vn dash. In these two small regions, take their value and just multiply by negative. So, for example, 0 minus 0 is, 0 multiplied by negative 1 is just 0. Here, for example, let's say 0.7, so minus 0.7, 1, so it's minus 1. 1.7, it will be here, minus 1.7. So basically, take this one and multiply by negative. So just flip it. So this is exactly the flip of this one. The same in that region. Take any value here from Vn dash and multiply by negative. Or if you like to deal with Vn, not Vn dash, you know that Vn dash is just equal to minus Vn. So instead of saying Vo is equal to minus Vn dash, it will be Vo is equal to Vn. Where is Vn? This is Vn. So copy and paste these two, you know, in here. Okay. Now let's go to the region from here to here in which Vn is larger than 1.7 or Vb plus 0.7. In that region, VO is equal to minus 0.7 minus VB, which is these 2 points here. Just connect them like this. This value here, minus VB, minus 0.7. And VR is equal to Vn dash minus 0.7 minus VB. So from here to here, these any point here, just subtract from it 0.7 and subtract VB. So here, for example, the input dash, V input dash is exactly equal to VB plus 0.7. So subtract these two, so 0 and 0. And again, for any value until you reach V maximum, V max. So this will be V max minus VB minus 0.7. So basically, this point. Basically, take this one and put it here. This is exactly this. And this thing here is exactly flipped here. Because VO minus Vn dash. Okay. So that's basically the negative. So look at the output. The output is clipped, but at the negative period. I'm sorry, negative half cycle. So this is negative clipping. Can we have both at the same time? Yes, you can have both at the same time. So this is called two-way clipping. So in the two-way clipping circuit, you have the resistance, you have the input, this guy here, and you have the two branches. And Mr. Diode. So if this is V1, if this is V2, if this is D1, this is D2. I will not analyze it. This is for you to do at home, okay? But you will just, mix up the two positive clipping and negative clipping problems into this one. I think so. I didn't do it by my hand, or I did. Yes, I did. Yeah, it's just the same. Just to combine both together. The positive clipping and the negative clipping. So in the positive half cycle, the clipping will happen at 0.7 plus V1. So this branch will cause positive clipping at the positive half cycle. And you will see that the voltage output is in the positive half cycle is in that shape. And this is basically V1 plus 0.7. And this thing here is exactly this. What should be the output of the resistance? It should be the rest of the dome. This thing here will be copied here. What is the value of this maximum? It is V max minus the corresponding point here because of Kirchhoff. So minus V1 minus 0.7. How about the negative half cycle? So this guy here will make the negative clipping. In general, V1 and V2 might be not the same, so I'm just choosing another point. Maybe this point is fine. And make the clipping at that point. So this stuff here is exactly this one. And the point, this point is minus V2 minus 0.7. What should be the output on the resistor? It should be this thing. This is minus Vmax. So this is minus Vmax plus V2 plus 0.7. So that if you take this point and add this value, so minus Vmax plus V2 plus V0.7 minus V2 minus, this will go with this will go with this, it will be minus Vmax, which is this one. This is Kirchhoff. Okay, so we're gonna see this today in our lab. Guys, you have a question? Train yourself a lot, solve a lot of examples, okay? And I'm sure you will be fluent with the rules that I'm telling you, with a way of plotting, sketching, analyzing. Just solve a lot